The magazine for automatic feeding of bars is a mechanized system designed to continuously supply steel bars to the processing line. The BBS Brown Boveri installation inductively heats steel bars using 1,450 kilowatts power at 500 Hz, preparing them for the forging process. The FICEP hydraulic press shear is a high-powered machine designed to accurately cut heated steel bars with diameters up to 130 millimeters, ensuring precise lengths for subsequent forging operations. The EUMUCO hydraulic press, designed for forging steel shell casings up to 50 kilograms, includes a 630-ton compression and broaching unit and a 200-ton drawing unit for precision calibration. The unit of the EUMUCO hydraulic press applies a force of 630 tons for compression and push broaching, shaping steel shell casings with high precision. It features a drop hammer traverse of 1,250 millimeters, ensuring deep penetration and accurate deformation of the material during the forging process, crucial for producing robust casings. The drawing unit in the EUMUCO hydraulic press uses 200 tons of force and a 3,200 millimeters drop hammer traverse to calibrate forged shell casings. Equipped with precision rolls and rings, this unit ensures the casings achieve exact dimensions and uniformity, critical for maintaining structural integrity and performance standards. The drawing unit in the EUMUCO hydraulic press uses 200 tons of force and a 3,200 millimeters drop hammer traverse to calibrate forged shell casings. Equipped with precision rolls and rings, this unit ensures the casings achieve exact dimensions and uniformity, critical for maintaining structural integrity and performance standards. The mechanical processing line precisely machines shell casings using programmable lathes for turning and finishing to meet exact specifications. The GF programmable hydrocopying lathe efficiently turns shell casings, using advanced automation for precise, high-speed machining and consistent quality. The final 130-to-1 programmable lathe performs precise final turning on the inner surfaces of shell casings, ensuring smoothness and dimensional accuracy. The highest raw material quality by strictly adhering to defined standards, selecting premium materials, and conducting thorough inspections to meet rigorous specifications for optimal performance and durability. Employs cutting-edge CNC technology for precision turning and grinding operations, ensuring high accuracy, efficiency, and consistency in producing complex gear components with exceptional surface quality and dimensional precision. Klingelnberg's fully automatic tooling setup uses Chemo's calculations to optimize precision and efficiency, reducing setup times and enhancing accuracy. Face-hobbing C300 machine, the largest of its kind, enables precise and efficient gear cutting for large-scale applications. Integrated manufacturing uses a reliable, closed-loop concept, ensuring continuous feedback and adjustments throughout production. This approach optimizes process efficiency, maintains consistent quality, and reduces errors by integrating real-time data analysis. Quality assurance utilizes state-of-the-art measuring centers, providing precise and comprehensive inspections to ensure the highest standards of gear component accuracy and performance. Heat treatment facility processes up to 140 tons monthly. Boasts extensive experience and metallurgical expertise, leveraging deep knowledge in material properties and processing techniques to ensure superior gear performance, durability, and reliability across diverse applications. Evaluates and documents the physical contact pattern, ensuring optimal gear meshing and performance through detailed analysis and reporting. Employs an economical grinding process for bevel gears up to 1,100 millimeters, combining cost efficiency with precision. This process ensures high-quality finishes and performance while optimizing production costs and time. Utilizes advanced grind-burn detection technology for all ground bevel gears, identifying potential heat damage or defects to ensure high-quality gear performance and prevent premature failure or operational issues. Uses magnetic particle testing to detect surface cracks, ensuring early identification of defects and maintaining gear integrity and reliability. The Koffler 50-feet lathe stands out as a marvel of industrial engineering, demonstrating its immense capabilities through a range of complex machining tasks. This extraordinary lathe is equipped with a 10-foot, four-jaw chuck and features a 12-foot swing, providing it with the flexibility and size needed to handle substantial components. With an impressive 50 feet between centers, it is particularly adept at managing large-scale projects that require precision over extended lengths. One of the key attributes of the Koffler lathe is its ability to turn with a remarkable accuracy of 0.0005 taper over a 3-foot distance. This level of precision is crucial when working on high-stakes components like the armature from a 9,000 horsepower motor, which is used to shred automobiles. The lathe's DC variable speed drive further enhances its versatility, allowing for smooth adjustments in speed to match the requirements of various materials and machining processes. In addition to automotive shredding machinery, the Koffler lathe has been employed in machining a stationary runner for a dewatering pump that was originally used in the historic Pearl Harbor. This task underscores the lathe's capability to handle specialized and historically significant components with the same precision as modern machinery. Perhaps one of the most impressive projects undertaken by the Koffler lathe involves machining a 10-foot diameter armature for a generator. Open die forging is a versatile metalworking process used to shape large, heavy metal pieces. On a 4,000-ton press, this technique becomes particularly effective for producing substantial components with precise specifications. In open die forging, a metal billet or ingot is heated until it reaches a malleable state. The heated metal is then placed between two dies that do not enclose it completely. Instead, the dies apply pressure to deform the metal and shape it into the desired form. Unlike closed die forging, where the metal is fully enclosed by the dies, open die forging allows for greater flexibility in shape and size. A 4,000-ton press is a high-capacity machine that can exert significant force, making it ideal for large-scale forging operations. This press can handle substantial billets and apply the necessary pressure to forge large components such as turbine rotors, crankshafts, or heavy machinery parts. The use of such a powerful press enables the production of forgings with high strength and durability due to the uniform deformation and refinement of the metal's grain structure. The process begins with the heating of the metal to the appropriate temperature, typically between 900 degrees Celsius to 1,250 degrees Celsius, depending on the material. Once heated, the billet is positioned on the press, and the dies apply compressive force to shape the metal. The operator may adjust the dies and pressure throughout the forging process to achieve the desired dimensions and characteristics. Open die forging on a 4,000-ton press is advantageous for producing large, complex components with a high degree of customization. It is commonly used in industries such as aerospace, energy, and heavy equipment, where the ability to create large, strong, and precisely engineered parts is critical. Steel making, ingot pouring, and forging. The first stage in crankshaft production is steel making, where raw materials like iron ore, coke, and limestone are combined in a blast furnace to produce molten steel. This steel is then refined in an electric arc furnace or a ladle furnace, where alloying elements such as carbon, manganese, and chromium are added to achieve the desired properties. The refined molten steel is poured into large molds to solidify and form steel ingots. Once cooled, these ingots are removed from the molds and prepared for forging. Forging begins with heating the ingots to a high temperature, typically between 1,200 and 1,300 degrees Celsius. At this elevated temperature, the steel becomes malleable, allowing it to be shaped without cracking. The ingots are then placed under hydraulic presses or hammers, which apply intense pressure to deform the steel into the preliminary shape of a crankshaft. The forging process is crucial for improving the mechanical properties of the steel. It aligns the grain structure of the material, which enhances its strength, toughness, and fatigue resistance. This step also reduces internal defects, voids, or inclusions that could compromise the crankshaft's performance. After forging, the crankshaft takes on a rough shape that will be further refined in subsequent machining operations. This preliminary forging stage ensures that the crankshaft will have the strength and durability required for high-performance engine applications. Machining is a critical step in the crankshaft manufacturing process, where the forged crankshaft undergoes precision shaping to achieve its final form and specifications. This phase transforms the rough, forged component into a highly accurate and functional part, ready for engine assembly. After forging, the crankshaft often requires a preliminary cleaning process to remove any scale or debris from the forging stage. This is typically done using abrasive blasting or chemical cleaning. The crankshaft is then inspected for any obvious defects or dimensional discrepancies. The first major machining operation is turning, which is performed on a lathe. The crankshaft is mounted on the lathe, and a cutting tool is used to remove excess material from the outer diameter, creating a smooth and accurate surface. This process refines the crankshaft's main journals and counterweights, ensuring they meet specific dimensional tolerances. Next, milling operations address the crankshaft's complex features. Milling machines cut away material to create the precise contours and profiles required. This step is crucial for shaping features such as the crank throws, which are offset sections that convert the piston's linear motion into rotational motion. Grinding is used to achieve a fine surface finish and precise dimensional accuracy. Crankshaft journals, which are the bearing surfaces, are ground to exact tolerances. This process uses a rotating grinding wheel to remove small amounts of material, ensuring the surface is smooth and within specified limits. The crankshaft's alignment and concentricity are carefully checked during this stage. Balancing is an essential part of the machining process. The crankshaft is checked for any imbalances that could lead to excessive vibrations or engine wear. Balancing involves adjusting the crankshaft's weight distribution by adding or removing material as needed to ensure smooth operation. Once machining is complete, the crankshaft undergoes a series of final inspections and tests. These checks include verifying dimensional accuracy with precision gauges, inspecting surface finishes, and conducting non-destructive tests, such as ultrasonic inspections, to detect any internal flaws. Once machining is complete, the crankshafts undergo rigorous quality control tests. These tests assess various factors, including dimensional accuracy, surface finish, and structural integrity. Crankshafts that pass these inspections are then prepared for dispatch. This involves cleaning, packaging, and labeling the finished products for shipment to engine manufacturers or automotive suppliers. Manufacturing and forging giant crane hooks involves a highly specialized and intricate process, essential for ensuring the strength and reliability of these crucial components used in heavy lifting operations. The process typically begins with the selection of high-quality steel, often alloy steel or carbon steel, which provides the necessary strength and durability. The steel is first heated in a furnace to a temperature where it becomes malleable. This stage is crucial as it allows the material to be shaped without compromising its structural integrity. Once the steel reaches the desired temperature, it is subjected to forging, a process where it is hammered or pressed into the rough shape of the crane hook. This is usually done using large hydraulic presses or forging hammers, which apply immense force to shape the steel. The forging process aligns the steel's grain structure, enhancing the hook's strength and toughness. After forging, the hook undergoes various stages of heat treatment, including annealing, quenching, and tempering. These processes are designed to relieve internal stresses, increase hardness, and achieve the desired mechanical properties. Flange forging is a critical process in the manufacturing of flanges used in various industries, including oil and gas, petrochemical, and power generation. Forging, a method of shaping metal through compressive forces, enhances the mechanical properties of the material, making it ideal for high-stress applications. This process involves several steps, from heating the metal to its plastic state to shaping it into the desired form. Flanges are mechanical components used to connect pipes, valves, pumps, and other equipment in piping systems. They provide a means to join parts together securely and are crucial for maintaining the integrity of fluid and gas systems. Forged flanges offer superior strength and durability compared to cast or welded alternatives. This is particularly important in high-pressure and high-temperature environments where reliability is essential. Ring forgings are used in applications that require a circular shape with high strength, such as turbine components, bearings, and various structural applications. The forging process ensures a uniform grain structure throughout the ring, enhancing its performance and longevity. Carbon steel is commonly used for flanges and rings due to its excellent machinability and weldability. It offers good tensile strength and can be treated to increase its hardness. Carbon steel flanges are often employed in less corrosive environments or where cost is a significant factor. Stainless steel is favored for applications requiring resistance to corrosion and high temperatures. It contains chromium, which provides excellent resistance to rust and oxidation. Stainless steel flanges and rings are used in industries such as chemical processing and marine environments where durability and corrosion resistance are paramount. Alloy steel includes additional elements such as chromium, nickel, and molybdenum to enhance its properties. This steel type is known for its high strength, toughness, and resistance to wear and impact. Forged alloy steel flanges and rings are used in high-stress applications, including aerospace and automotive industries, where enhanced performance is required. The forging process typically involves heating the metal to a temperature where it becomes malleable, then shaping it using a hammer or press. This can be done through various methods, including open die forging, closed die forging, and ring rolling. After forging, the component may undergo additional processes such as machining, heat treatment and surface finishing to achieve the final specifications. This method involves compressing the metal between flat dies. It is often used for larger or simpler components where precise control over the shape is less critical. In this process, the metal is enclosed within a die cavity and shaped by pressing. It allows for more complex shapes and tighter tolerances compared to open die forging. Ring rolling is a specialized technique used to produce ring-shaped forgings. The metal is heated and then rolled between two rotating rolls to achieve the desired ring dimensions.